In this video, you're going to learn how to do partial fraction decomposition. We're going to be going through all the different types. We're going to be talking about linear factors, repeated linear factors, quadratic factors, repeated quadratic factors, as well as improper fractions. And a lot of the different types, we're going to be going through more than one example, so you get a lot of experience with how to approach these problems. So let's get started with the first example. Now, what I want to show you first is that you're familiar with combining fractions. So if you have, two fractions, you want to combine them into one fraction, what do? Well, you want to get a common denominator, right? So you get that common denominator, you combine these together, and you've got it, right? But what partial fraction decomposition is you're actually doing that process in reverse. They're giving us this fraction here, and we want to break it down to the 2 or 3 or 4, or however many original fractions that there were that would assemble to give us this fraction here. So the first thing you want to do when you do partial fraction decomposition is you want to factor the denominator. So if I do that, this denominator would factor to x minus 4 times x plus 1, and the numerator is 5x minus 3. Now, again, remember we're working backwards. We want to find out what those original fractions were before, we assembled them, okay, into one fraction with a common denominator. So you can see that one of the denominators could have been x minus 4. One of the denominators could have been x plus 1. Now, we don't want these fractions to be improper, meaning that the degree in the numerator should be lower than the degree in the denominator. See how this is x to the first? That means this must be a constant a. This is x to the first. This must be a constant b. Now, we have to figure out what those a and b values are. And the way we're going to do that is we're going to clear the denominators. We're going to multiply through by the common denominator so that we can more easily solve this equation. So the common denominator you can see is x minus 4 times x plus 1. So we're going to multiply everything by x minus 4, x plus 1. So I'm going to distribute that to the left and right sides of the equation to keep it balanced, right? And so if we do that, when you distribute here, the numerator and denominator are going to cancel, leaving us with just 5x minus 3. Over here, you can see the x minus 4s would cancel, but we have a times x plus 1. Over here, when we distribute, you can see the x plus 1s cancel, and we just have b times x minus 4. Okay, so are you with me so far? So we've cleared the denominators. Now, there's a couple different ways to do this problem. So let me see if I can show you one technique first, okay? And then in the second example, I'll show you another technique. So the first technique I want to show you is where you pick strategic values for x. Now, what do I mean by picking strategic values for x? So say, for example, we let x equal -1. Okay, what happens when you let x equal -1 is that's going to make this 0 times a is 0. This term is going to cancel out. Now you can see you've got -5b. If we put -1 in here, we get -5 minus 3 is -8. So this way we can solve for b by dividing both sides by -5. And you can see that b is equal to 8/5. Okay. Similarly, if we want to set x equal to 4, let x equal 4, that's going to cancel out this quantity. 4 plus 1 is going to give us 5a, which is equal to 20 minus 3, which is 17. And if we divide both sides by 5, you can see that a is equal to 17/5. Okay, so you're with me so far? So now what we want to do is we just want to put these back into the original fractions here. So we have 17/5 over x minus 4 plus, okay, b was 8/5, all right, over x plus 1. And then you can take this a step further by, you see how you could factor out like a 1/5. So if we did that, this would be 1/5 times 17 over x minus 4 plus 8 over x plus 1. And if you combine these together, you're going to get back this original fraction right here. So that's example number 1. We're going to do another example working with these linear. See, linear just means first degree factors. And let me erase this board and I'll be back with you. Okay, example number 2. Again, the first step is you want to factor this denominator. So if we do that, we get, let's see, 2x and 1x, and we get positive 5 and negative 3. So that gives us negative 3x plus 10x, which is 7x, right? Okay, and the numerator is 6x minus 22. Now, what we want to do is we want to figure out what were those original fractions before we combined them and we got this just one fraction, right? So we're trying to do the partial fraction decomposition. And so what I'm going to do is I'm going to write these linear factors. Linear just means that they're to the first degree, like a line, right? But again, we don't want these to be improper fractions, so if this is x to the first, this must be x to the 0, meaning that these are constants. Now you could put a here and b here, it doesn't really matter, but you want to make sure that these are 1 degree lower. Okay, so now what we're going to do is we're going to do just like we did in the last example. We're going to clear the denominators by multiplying through by the common denominator. Okay, so if I take this and I distribute it to each one of these fractions, we can clear the denominators. So 2x minus 3 times x plus 5 times this one, see the numerator and denominator are going to cancel, just leaving us with 6x minus 22. When we distribute it to this one, the 2x minus 3's cancel, and we have a times x plus 5. And when we distribute to this one, the x plus 5's cancel, so we have b times 2x minus 3. So are you with me so far? Okay, so now I told you in the first example we could pick strategic values for x. So in this example, you know, you could do -5, or you could do x equals 3/2. But I'm going to show you a different method here. So what you're going to do here is you're going to distribute and you're going to collect like terms. So you've got ax plus 5a plus 2bx minus 3b is equal to 6x minus 22. Now if we collect the x terms, what you have is ax plus 2bx. If you collect the constant terms, that's 5a minus 3b. I'm going to factor out the x here, so that's going to give us a plus 2b times x, and this is going to give us 5a minus 3b, and this equals 6x minus 22. So now what we're going to do is we're going to say, all right, the coefficients in front of the x must be equal to the coefficient on this side in front of the x. So that means that a plus 2b is equal to 6. And the constant 5a minus 3b must be equal to negative 22. So all we have to do now is solve that system of equations, find our a and b, put them back in, and these are going to be our partial fractions that add up to the original fraction. Okay, so you're with me so far? So what I would do here is I'd multiply this top equation by 5. So that's going to give you 5a plus 10b is equal to 30. And if you combine those together, or I should say we subtract those, so 5a minus 5a is 0, negative 3 minus 10 is negative 13b, and negative 22 minus 30 is negative 52, right? So if we divide both sides by negative 13, that comes out to b is equal to 4. That worked out pretty nice. So if we put 4 back in to any one of these equations, I'll just put it into this one here, that's going to give us a plus 2 times 4 is 8 equals 6, which means that a is equal to negative 2. And then the last step, and sometimes students forget this, is that you want to put these back in because, you know, one of your classmates might have made this a and this one b, and so your teacher wants to see what are those, you know, actual fractions. Okay, so you want to write those, you know, back in there. So negative 2 times 2x minus 3 plus b is 4, which is 4 over x plus 5. And if I really wanted to be a little bit neater about this, I'd probably put the positive one first and then subtract 2 over 2x minus 3. Now the nice thing about partial fraction decomposition is you could check your work. You could say, well, let me go ahead and get common denominators, combine these into one fraction, see if I get back the original, and that wouldn't be a bad way just to practice to see, you know, if you're on the right track. So this is working with the linear factors. Okay, the next one we're going to do is repeated linear factors. Let me erase the board and I'll be back with you. Okay, in this example we have what is called a repeated linear factor. So linear means it's to the first degree, like a line. Repeated, you can see it's to a higher power than 1. So it could be squared or cubed and so on. So what we're going to do here is we're going to look at this and say, well, the original fractions could have had a denominator of x minus 2 or x minus 2 squared, right? So when you combine these together, what's the common denominator? If you had x minus 2 and x minus 2 squared, well, the common denominator would be x minus 2 squared. You would have to multiply this fraction by x minus 2 over x minus 2, so you have that common denominator, you combine them together, right? So what we're going to do now is we're going to put a here and b here. Now, sometimes students get a little bit confused by this, and because they see that this is x squared, and they said, well, you told us that you want this to be 1 degree lower than the denominator. Well, you're just looking at the quantity that's inside of the parentheses. That's what you want to be 1 degree lower. So this is x to the first, this is x to the 0, it's a constant. So we'll talk about quadratic terms as we go through this video. Okay, but so these are going to be our partial fractions, but what we want to do now is we want to clear the denominators by multiplying through by the common denominator. So if I distribute that to all of these, okay, left and right side to keep the equation balanced, that's going to cancel out these denominators, Okay, one of these x minus 2's cancels one of these, leaving one left over. And then here they both cancel out, so you just have b. So now you've got a couple of options here. I think what I'm going to do here is I'm just going to pick, I think maybe I'll just distribute. So this is just going to be, let's see, ax minus 2a plus b is equal to 7x minus 11. So you can see that a must be 7, right? Because the coefficient in front of the x matches the coefficient in front of the x over here. So that means that a is equal to 7. And then over here we have an equation, negative 2a plus b is equal to negative 11. So negative 2a plus b equals negative 11. If we put 7 in for a, that gives us negative 14 plus b is equal to negative 11. Add that 14 over, and you can see that b is equal to 3. So now we've got a and b. Let's go ahead and rewrite our original fractions here. So 7 over x minus 2 plus 3 over x minus 2 squared, and that's what your teacher's going to want to see. Now, if you want to check your work, you can go ahead and get a common denominator by multiplying these by x minus 2 over x minus 2. Then you have a common denominator, combine them together, and you should get back 7x minus 11 over that common denominator. So I'm going to erase the board. We're going to do another example talking about repeated linear factors. And okay, example number 2 of the repeated linear factors. Okay, so what we want to do, remember, is factor the denominator first. If you want to try this one on your own, go ahead and give it a go. The first step though here is I'm going to factor this denominator by factoring out a greatest common factor, okay, like so. Then we can factor this a little bit further. You can see this is going to factor as x minus 3, the quantity squared, and you can see that's where our repeated linear factor is coming in. So let me go ahead and rewrite this. We've got 3x squared minus 24x plus 53x all divided by the common denominator, or I should just say the factor denominator. And so what we want to do now is we want to work ourselves backwards and say, well, what were those original fractions before we combined them and we got this up here, right? So you can see one of the denominators could have just been x, right? One of the fractions could have had a denominator of x minus 3, and one of the denominators could have had x minus 3 squared. So when you combine these together, what's the common denominator? It's x times x minus 3 squared. So the key when you have a repeated linear factor is you want to include not just x minus 3 squared, but also x minus 3 to the first, because when you combine these together to get a common denominator, you're going to get that x minus 3 squared. So if you're working backwards, we don't know. I mean, it's possible that this term could actually be 0, and maybe we just have this fraction and this fraction, but we won't know until we sort this out by clearing the denominators and solving. So again, our numerators are going to be a, b, and c this time. And again, it's just 1 degree lower. That's x to the first, so that's going to be x to the 0, and so on. So let's go ahead and multiply through by our common denominator, which is going to be this right here. Okay, so if we multiply everything by that common denominator, you're going to be left with 3x squared minus 24x plus 53. Let's see, did I make a mistake? This is plus 53, not supposed to be 53x, it's just plus 53. Okay, equals, and this is going to be a times x minus 3 squared, okay, because you can see the x's are going to cancel one another out, plus b times x minus 3 plus, let's see, also we have an x here, right? And then over here we have plus cx. Okay, so we multiplied through by the common denominator to clear the denominators. Now we have a little bit something easier to work with. And what we can do here is we can pick some strategic values. Let's go ahead and do that method for this one. So let's just go ahead and let, I'll just put over here, let x equal 0. Okay, so if we let x equal 0, 0 times anything makes this term 0, this term 0. Negative 3 squared is 9a, 9a. This would be 0, and this would be 0, so you get 53. Okay, so if we divide by 9, you can see that, a is equal to 53/9. Not a super great number, but that's okay. That's just how this particular one's working itself out. Now, let's say if we do x is equal to 3. So let x equal 3. If we do x equal to 3, that's going to cancel out this term and this term. So we're going to end up getting 3c is equal to, well, let's see what this side is. This would be 27 minus 3 times 24 is how much? Let's see, that's 72, right? Plus 53. Okay, so we've got some challenging math here. Let's see if we can simplify this. That's 80 minus 72, which is 8, right? So c is equal to 8 thirds. Okay, now we just have to solve for b. Now, what you might want to do at this point, there's nothing else that we can cancel out by picking strategic values. Just pick a small value of x, like let x equal 1. So if we let x equal 1, let's see, what does that give us? That gives us 3 minus 24 is negative 21, plus 53 is 32, all right? And if we make this equal 1, we get 1 minus 3 is negative 2. Negative 2 squared is 4. 4 times a is going to give us, let's see, what would that be? That would be 4 times 53 ninths, which is 212 over 9. Okay, plus 4 minus, let's see, 1 minus 3 is going to give us negative 2 times 1 is negative 2, negative 2b, okay, plus negative 2b, plus, now we've got our c value, which, let's see, c we know is 8/3 times 1, so that's 8/3. So then what you would do is you would go ahead and solve for b, and then you know what a, b, and c are, and you want to put them back into those fractions. So this particular problem I just made up off the top of my head. Some of the numbers got to be a little bit more challenging, but I want to show you the process. So let's go ahead and get into the next one, working with quadratic factors. Let me clean the board and I'll be right back with you. Okay, in this example, we're going to be working with quadratic factors. Now you can see this problem here, it's already factored for us, but what we're going to do is we're going to go ahead and break it up into its two fractions here, x squared plus 3 and x plus 5, okay? So sometimes you have to factor the denominator. In this case, they already gave it to us in factored form. But the question is now is, what is the numerator, okay, of these fractions? Well, this one's going to be ax plus b. This one's just going to be c. Now, why ax plus b? Well, this is x squared. So this always wants to be 1 degree less. If it was the same degree or higher, then that's considered an improper fraction. And we'll deal with those as we move through this video. This one's x to the first, so this is just a constant. That's x to the 0. All we have to do now is clear the denominators, okay, and solve for a, b, and c, and then we'll know what our original fractions were before they became this larger fraction, okay? So that's called partial fraction decomposition. So let's go ahead and multiply through by the common denominator. It's a lot of arithmetic, and again, you have to be careful you don't make some simple mistakes. But if we distribute everything, okay, this to every term, left and right sides, that's going to give us 6x squared plus 21x plus 11. Here the x squared plus 3's are going to cancel. We have ax plus b times x plus 5, right? And then over here we've got c times x squared plus 3. Now, we've got a couple different options. We could do the strategic method where we set x equal to negative 5, right? That would cancel out this term. We could solve for c and do it that method, or we could just FOIL this out, collect like terms, and make a system of equations. I think I'm going to do the latter method. So if we go ahead and distribute and FOIL this out, we get ax squared plus 5ax plus bx plus 5b plus cx squared plus 3c equals all of this, right? We're going to collect like terms, so we've got, I'm going to collect the x squareds. Okay, so that means a plus c times x squared. I'm going to collect the x terms. So that's going to be 5a plus b times x. And then I'm going to collect the constant terms, 5b and 3c. So 5b plus 3c. Now you can see, you can set these equal to one another. A plus c must equal 6. See how you set the coefficients in front of the x squared is equal? So that's one equation. A plus c is equal to 6. We've got 5a plus b is equal to 21, right? And we've got 5b plus 3c. 5b plus 3c is equal to the constant 11. All we have to do now is solve this system, and we know our a, b, and c. So should I go ahead and do this? Well, okay, let's see. So what's the strategic way to do this? Well, let's see. I think what I'm going to do is I'm going to do a little bit of a substitution technique. I'm going to say a is equal to negative c plus 6. So now I know what a is. I'm going to put that in for a right here. So that's going to give us, let's see, 5 times negative c would be negative 5c, right, plus 30 plus b is equal to 21. If I clean this up a little bit, that's b minus 5c is equal to negative 9. Okay, and then now let's look at the third equation. We've got 5b plus 3c equals 11. If we solve this by multiplying the top equation by 5, or maybe negative 5, negative 5b plus 25c is equal to 45. If we add those together, you can see you're getting 28c is equal to 56, so that means that c is equal to 2. Okay, so now if c is equal to 2, that means that a is equal to 4, right? A equals 4. And if a is 4, that means that's 20. That means that b must equal 1. Okay, so basically just solving a system of equations. But the last step, what you want to do is you want to put them back in so your teacher knows what the actual fractions are. So that's 4x plus 1 over x squared plus 3, right? Plus c, which is equal to 2 over x plus 5. Now, if you want to check your work, like always, you can go ahead and get a common denominator, combine these into one fraction, and you should get back that original fraction that we started with here. But this makes it a lot easier to work with when you're doing certain problems in calculus. So when you break it down, you know, these are a little bit simpler, and they're easier to work with when you do integration and other problems. So I'm going to erase this board. We're going to do another example with repeated quadratic factors, and then we'll keep going. Okay, example number 2 of the quadratic factors. Now remember, quadratic is a second degree. They've already factored this denominator for us. That makes it a little bit easier. But what we're going to do here is we're going to work backwards to figure out what those original fractions were before we combine them into this larger fraction here. So this is the partial fraction decomposition process. X squared minus 7 can't be factored any further. So this is a quadratic factor. Our numerator is going to be 1 degree lower, ax plus b. Now if this was an x cubed, then what I would have is ax squared plus bx plus c. So you want to start with whatever this degree is and then go descending until you get to a constant. If it was x to the 4th, you know, and you couldn't factor it, it was like a quartic factor, then it would be ax cubed plus bx squared plus cx plus d, right? So you start at a 1 degree lower and you go down to the constant. This one's just linear, x to the 1st, so this is going to be a constant. Now make sure you pick different letters. You don't want to use the same letter twice, okay? That's key also. But what we want to do here is we want to then clear the denominators by multiplying by that common denominator, which is going to be x squared minus 7 times x plus 1. If you distribute to each one of these factors, that's going to clear the denominators. And so that gives us 3x squared plus 5x minus 4 equals ax plus b times x plus 1, okay, plus c times x squared minus 7, because you can see the x plus 1s cancel each other out. So I'm going to do the same thing like I did on the last one, because we've got, you know, more variables. It's a little bit more complicated. So what I'm going to do is I think I'm just going to FOIL this out and make a system of equations. So if we do that, that's going to give us, let's see, ax squared plus ax plus bx plus b plus cx squared minus 7c, right? And that's equal to this right here. And if we collect like terms, we get a plus c times x squared plus a plus b times x minus 7c, right? Okay, so now what we can do is, oh, I forgot the b, didn't I? So plus b minus 7c. So minus, let's scratch this out. So that's going to be, let's see, plus b minus 7c. Okay, so you want to group the constants together. So now we can make a system of equations. We've got a plus c. See how that's the x squared is equal to 3, right? And then what else do we have? We've got a plus b is equal to 5. A plus b is equal to 5. And we've got b minus 7c. B minus 7c is equal to negative 4. Okay, so all we have to do is solve this system, and we'll know what a, b, and c are. We can put them back into these original fractions, and that's our partial fraction decomposition. So I think what I'll do here is I'll subtract these two equations here. So a minus a is 0. Then we get c minus b is equal to negative 2. And so now we have negative 7c plus b is equal to negative 4. I'm going to add these two equations together. That's negative 6c equals negative 6. So you can see that c is 1. If you put 1 back into any one of these equations, you can see a is equal to 2, right? And now we know a and c. So if a is 2, that means b must be 3. And you've got your a, b, and c. So all you have to do is go ahead and put them back into these fractions. So this is going to be 2x plus 3, right, all over x squared minus 7 plus c, which is 1, over x plus 1. And again, you can check your work by combining these together into, by getting common denominators, combine them into one fraction, you should get back this original fraction. So let me erase this board and we'll talk about the repeated quadratic factors next. And if you're interested and you're preparing for the SAT or the ACT or SAT, I've got 2 video courses available. Feel free to check those out. I'll have links to them in the description below this video. We go through a lot of different concepts, teaching, example problems, things that you would typically see on the test. So if you're interested in that, check that out. If you're interested in online one-on-one tutoring with me, you can also contact me about that, mariosmathtutoring.com, or through the About page on my YouTube channel, Mario's Math Tutoring. But let me erase this and we'll go through the repeated quadratic factors next. Okay, now we're talking about repeated quadratic factors, and again, in this example, they've already factored the denominator for us. If it wasn't factored, you would go ahead and factor it first, but you can see that x squared plus 2 can't be factored any further. So this is a quadratic factor, but it's repeated. See how it's to the second power, or if it's to the third power, or to a higher power than 1. What we have to do is we have to consider what those original fractions were with this repeated quadratic factor. So what our fractions are going to look like is they're going to be x squared plus 2, but also x squared plus 2 squared, and we also have this linear factor here, which is x plus 3. Okay, so you're with me so far? So basically, if you were to combine these together, all 3 of these, what's the common denominator? Well, you need 2x squared plus 2, and you also need an x plus 3. So if you were to get a common denominator, this one's missing another x squared plus 2, and an x plus 3. So you have to consider that there could be both of these terms, or it could just be this term. This one might be equal to 0. We won't know until we solve this, this equation here. So the numerator, though, remember, this is going to be 1 degree lower. So this is going to be ax plus b. This is going to be cx plus d. This one is just going to be e, because this is a linear factor, that's first degree. This is a constant. This is second degree, so that's first degree, second degree, first degree, right? So you want it to be 1 degree lower, and you want to go in descending order to the constant. So it's possible that some of these values, a, b, c, d, e, could be 0, but we won't know again until we solve this. So what we're going to do is we're going to multiply through by the common denominator. This is the common denominator. So if we multiply everything by this, that's going to cancel. So you're going to get 3x to the 4th. This one's a big one. This is a monster problem. You can see they're getting a little bit more difficult as we go through. This one here, you're going to have ax plus b, right, times what? Well, we canceled out one of the x squared plus 2. We're going to have another x squared plus 2 as well as an x plus 3. This one, we're going to have cx plus d, okay, times x plus 3, right? And then this one, we're going to have let's see, e times x squared plus 2 squared. Okay, so this one is it's a monster, it's a giant. Okay, and so I don't know if I'm even going to solve this one for you guys, but what I'm going to tell you is that I would FOIL this out, multiply all this out. I would collect like terms, and I would set all the coefficients in front of the x to the 4th equal to 3. That would be one equation. Then I would set all the x cubes equal to -2, and so on, like we did in the previous example. But what I wanted to point out is that when it's a repeated quadratic like this, you have to consider that it could be x squared plus 2, x squared plus 2 squared. If this was x squared plus 2 cubed, then we would also have x squared plus 2 cubed. You want to consider all those cases, because we really don't know, what the original fractions were before we combine them, and that's what we're doing. We're working backwards. So I'm going to let you do the arithmetic on this one. Send me a text, or not a text, but send me an email or a comment, below if you solve this. Let us know what a, b, c, d, and e are, and what the partial fractions are. And I'm sure people that watch this video will appreciate that. But what we're going to do now is we're going to talk about the improper fractions and how to handle those. So let me erase this board, and I'll be right back with you. Okay, the last type of partial fraction decomposition problem that we're going to work with today is when you have an improper fraction. Now, how do you know how to recognize an improper fraction? Well, that's when the degree, okay, the power in the numerator is either the same as the highest powered term in the denominator or greater, okay? Sometimes students don't realize that if this is like actually the same, like these are both the same degree, that's actually considered improper, as well as when the degree in the numerator is greater than the denominator. So what you have to do in a situation like this is do polynomial long division. So what I'm going to do is I'm going to take x squared minus 2x minus 3, see how many times that it goes in to x cubed plus 0x squared plus 0x plus 3. Okay, so polynomial long division. So x squared goes into x cubed x times, right? So if I distribute x, I get x cubed minus 2x squared minus 3x. If you need a reminder on how to do this polynomial long division, I have a video on it on my channel, Mario's Math Tutoring, but I'm just kind of doing this to show you this process. Now, how many times does x squared go into 2x squared? That's 2. So if we distribute, we get 2x squared minus 4x minus 6. If we change the signs to the opposite and add, that gives us 7x plus 9. But what do you do when you have the remainder? You put the remainder over the divisor, which is x squared minus 2x minus 3. Now, what we want to do is we want to do the partial fraction decomposition on this remainder portion. So what I'm going to do is I'm going to factor the denominator, x minus 3 and x plus 1, and we're going to break this up into its partial fractions. So 7x plus 9 over x minus 3, x plus 1. And that's going to equal, let's see, a over x minus 3 plus b over x plus 1. Okay, so now all we have to do is multiply through by the common denominator, which is x minus 3, x plus 1, right? If we distribute that to each term, we're going to get 7x plus 9 equals a times x plus 1 plus b times x minus 3. And here I'm just going to pick the strategic value. So if x equals negative 1, that's going to give you 2, because I'm putting negative 1 in for x. That's going to give us 0. That's going to give us negative 4b. So that means that b equals negative 1/2. And if I let x equal 3, that's going to be what? That's going to be 30 is equal to 4a. And this is going to cancel out and give us 0. So that means that a is equal to 34, which is 15/2. Now all we have to do is put them back in here. So we've got, let's see, 15/2 over x minus 3. Let's see, minus, because this is a negative 1/2, so minus 1/2 over x plus 1. But you can see you can factor out a half. So this would be 1/2 times 15 over x minus 3 minus 1 over x plus 1. But you also have x plus 2. So the idea here is that if you were to add all this together, okay, add all this together, get common denominators and so on, you're going to get back to this original fraction. But this is the partial fraction decomposition. We had to start by doing the long division because the degree in the numerator was the same or higher than the highest power in the denominator. But then what we had to do is we had to take the remainder, okay, this fraction here, and do the partial fraction decomposition on it. So I hope this helped you to understand how to work with partial fraction decomposition better. Subscribe to the channel. Check out more math videos on my Mario's Math Tutoring YouTube channel, and I look forward to helping you in the future videos. I'll talk to you soon.